This video is about potential energy, which is the stored energy due to position or condition. Position would be like lifting a weight above the ground. If you lift a weight above the ground, well, that weight can do work. So that weight has energy. Anything that can do work has energy. A weight above the ground, you could tie a rope to it, put it around a pulley, and you could lift things up. Condition would be like a spring. If you stretch or compress a spring, there's energy in that spring because that spring could do work. It could apply a force and make something move, or apply a force and work against the motion of an object and stop it. The equation for potential energy is mgh, where m is mass, g is the acceleration due to gravity, and h is height. And because mg equals force of gravity, this also is the equation. When you do work on something, you change its potential energy. With positive work, again, just like before, where the angle is zero, like lifting up an object, when the work is positive, when the angle between the force and the direction of displacement is 0 degrees, like lifting up barbells. Okay, work is positive when theta equals 0 degrees. And the direction of the force, direction of displacement, the angle between them equals 0 degrees, lifting up a barbell. When you bring that barbell down, you're doing work as well, but now the angle is 180 degrees, and the angle between the direction of the force and the direction of displacement, so the barbell goes down. When you bring it down, your force is up, and the angle is 0 degrees, so work is negative because the cosine of 180 is -1, and over here the cosine of 0 degrees is just 1. So you have a 1.6 meter person lifts a 2.1 kilogram book above the ground, 2.2 meters. How much work is done? Well, the work equals the change in potential energy, and that's what we set up here. When you work on an object, you change its potential energy, whether it's lifting it up, or bringing it down. So that would just be m, g, h, and we used m because we have m. So the m is 2.10. So when we multiply it by g, you get 21 newtons, and you lift it 2.20 meters above the ground. Work is the change in potential energy, and 21 times 2.20 is, let's see, 46.2. The work is 46.2 joules. It's 46.2 joules, or 46.2 Newton times meter. All right. Now, a spring can have another kind of energy due to its condition. If it's compressed or stretched, it can do work because it can apply a force and make something move, or it can apply a force and act against the movement of an object. Potential energy is average force, I'll put a line over that, times the stretch. So the potential energy depends on the average force you needed to stretch that spring, and the distance of the stretch. X is the stretch or the compression, F is the average force, put a little line over here. Um, Most of the springs we'll be dealing with are ideal spring, where force and stretch are directly proportional. And this is what it looks like when two things are directly proportional, force and stretch. This is an ideal spring, and the slope of that ideal spring is what's called the spring constant, and it quantifies the rigidity of a spring. Constant quantifies, gives a number to, quantifies rigidity of the spring. So a spring with a big spring constant is a very rigid spring, and even just a little bit of stretch or compression would store a lot of energy. If it had it has a small spring constant would be like the little spring in your pen. So potential energy, because when you stretch and compress the spring, there are a lot of forces, but the force we use is the average force. So the potential energy stored in the spring depends upon the average force to stretch it times the stretch, and I think I'm going to not go into the derivation. That turns into this, where K is the spring constant. And this is the most popular form of this equation, that the potential energy of the spring depends upon the rigidity of the spring, K, and how much you stretch it. And what's that relationship between potential energy and stretch or compression? It is a direct square relationship. Let's write direct square. And so a direct square plot looks like this. There's an exponential plot. Maybe in math class, this is second order exponential. You've got a spring with the following spring constant. It takes 53 newtons to stretch it 1 meter, and it hangs vertically on a ruler. At the end of the ruler is next to 15 centimeters, so that would be really your zero mark. The hanging spring that's uncompressed, at the bottom is right on the 15 centimeter mark. You've got a 2.5 kilogram mass attached to the end of the spring. Where will the spring line up against the ruler? So that's really, I need to determine the stretch. K equals F over X. The spring constant is the ratio of the force to the stretch. We are told the spring constant is 53 newtons per meter. And the force is, well, I'm going to multiply this by 10, 25 newtons. And the stretch is what we don't know. And when you solve for this, you get a stretch. Now, we're going to get a stretch in meters because that's what the spring constant is. I'm going to look at my key here, right, because I've done the calculations already. Okay. And the spring constant, whoops, looking at example two. Okay, good. So the stretch is 0.47 meters because this is in meters, but that's not the answer. It says, where will the end of the spring line up? Well, the spring start at the 15 centimeter mark, and that's what 15 centimeter is 0.15 meters. And when you add it all together, you get 0.62 meters. That's where the end of the spring is because it started here, and here's the stretch. So now the end of the spring will be 0.62. If you're given a force versus stretch plot, the potential energy is the area of the triangle under the plot. So what's the potential energy here? Potential energy, remember we said is average force times x, so it's the area. So it is 1/2 base times height, that's a triangle. 1/2 base is 6 meters. Substitute with units, and the height is 2 newtons. And that turns out to be a potential energy stored in that spring at that stretch of 6. At the stretch of 6 turns out to be 1/2 of 6 is 3, so 6 joules or 6 newtons times a meter. Let me see if I've got the significant digits. Well, all right, they've got one significant digit in the picture. Okay, 15 joules of energy stored in a stretched spring. What is the value of the spring constant? So we go right away to the equation that we got in the previous page. Why? Because they've given me the PE and they want the K, spring constant. That's K. This is PE. And the stretch, well, the stretch is the difference between what it is with nothing on it, it's zero point 0.5, and then you put something on it's 1. So the stretch is 0.50 meters. So put the numbers into the equation. 1/2 K is unknown, 0.50 meters squared. So I multiply both sides by 2, I get 30 equals K times, oops, that's squared 0.25. Divide both sides by 0.25 and I get 120 newtons per meter. That's the K value, the ratio of the newtons per meter. There you go. It would take 120 newtons to stretch this spring 1 meter, or 60 for a half, 30 for a quarter. This one is getting a little ahead of ourselves, but that's okay. We don't want to This is called conservation of momentum. You've got a car with a certain mass and a velocity. Now, it has what? It has kinetic energy. You have not learned kinetic energy, but we'll do a little kinetic energy rather than leave this and come back. So it's got this velocity, so it's got moving energy, and it strikes a coiled spring, and it's brought to rest. Why it was at a certain distance? Why was it brought to rest? Because the kinetic energy turned into potential. So we'll say kinetic energy, which you haven't learned yet, so don't worry about, equals the potential energy of the spring. So 1 half mv squared. You'll be learning that's kinetic energy. Or maybe you learned it in middle school. Equals 1 half spring energy kx squared. So the halves cancel out. And the mass that we're given is 1200 kg. And the velocity now, here's a problem. We've got to change that over 60. We've got to take that 65 kilometers per hour, do a little conversion. I want to get rid of kilometers, so I put it in the bottom so they'll cancel. 1,000 meters. Then I've got to cancel the hours. 1 hour. 1 hour, let me erase that. 1 hour on the top, so it cancels, is 3,600 seconds. 60 times 60. And this velocity turns out to be, I'm going to have to take out the calculator, pause this and take out the calculator. All right, so the conversion turns out to be that the velocity is 18.05 meters per second. So that's 18.05 meters per second. All of that is squared equals k. What is the spring constant? K times x squared. Now what's the x? It's stretched 2.2 meters squared. And the k turns out to be, with two significant digits, 8.0 times 10 to the fourth newtons per meter. There you go. So to go over this again, the car had kinetic energy, and then it hits the spring, and that turns into to potential energy of the spring, 1 half kx squared, and the k is the answer. We'll get into this conservation of energy. This is what this is. Energy can't be created or destroyed. Where did the where did the kinetic energy, moving energy, go and hit the spring? It turned into potential. We'll talk more about that later, so don't worry about that, okay?